anything for a whole minute. All right, but we're going to talk about efficiency. Efficiency. Well, as you can imagine, efficiency becomes a big deal, right? Because when you go to buy a car, what is one of the things you look at? Fuel economy. No, I cared. Mine has direct injection, so it gets a lot better. What?
Yeah, you're looking at how many miles can you get.
How many miles you get? Well, okay, so you want the same things in it. I mean, you want to talk about a group of people who are over the top anal about fuel efficiency. It's usually pilots. I don't know why, but they really are. You know.
Because if you run out of fuel in the air.
No, they want to see how far they can stretch it, and they're cheap. We're cheap people. I'm not they. We. All right. So, but I'm a mechanic, so I always think different. I don't think like a pilot. I think of a mechanic. I'm like, oil and fuel are cheap. I want to run my engine so it lasts. So, all right. We're going to talk about thermal efficiency. Thermal efficiency. Thermal efficiency. All right. So we said a recip engine is what kind of engine? It's what? Recip engine. Heat engine. Engine is a heat engine. I said it twice now. He is a heat engine. All right. Because heat produced by burning fuels in the cylinder causes expanding gas that does the work. I'll write that again. I don't need to write that again. I already said that once, right? Yeah. Heat produced by burning fuel in the cylinders causes expanding gas that does the work. What work does it do? What does it push on? Piston. The piston pushes on the connecting rod is in between. Piston pushes on the connecting rod. It's like a little song, you know. The piston is connected to the piston pin. The piston pin's connected to the connecting rod. The connecting rod's connected to the. Okay, he's going. Okay, he's not my dad. I just made it up. All right. Wait, what was that?
Yeah, those were her lullabies.
No, we talked about the invisible spiders that would bite her and she would swell up and die if she stepped out of bed. So. All right, so heat work. So it's a heat engine, so it's doing heat work. So heat work can be expressed as the British thermal unit. British, B-R-I-T-I, the British thermal unit. And somewhere there's a joke about, I'll have to make one up, but I can't do it on the fly, a BTU, the difference between a British thermal unit and like a redneck thermal unit. There's got to be some joke in there. Come on, help me out with that.
A freedom thermal unit?
Yes, thank you for remembering that. Okay, the freedom thermal unit. No, that was French. You said freedom thermal unit?
Yeah.
That was the French.
Oh.
We changed French fries into freedom fries. All right. Okay. So we have this thing called a British thermal unit. Now I'm going to tell you, you got to know what a British thermal unit is because I promise you it will be on an FAA test. It was in fact, and everybody knows I used to be a mechanic examiner, and you have to do an oral and practical. It was one of the oral questions. Describe a British thermal unit. So you have to know what this is throughout the entire thing. So a British thermal unit, a BTU, a BTU, equals the heat required. Does anybody know it?
1 pound of water, 1 degree Fahrenheit.
To raise 1, he is correct, pound of water, 1 degree Fahrenheit. I'm just going to put F, 1 degree F, mostly because I don't. Also equals 778 foot-pounds, FTLB, foot-pounds of work. This is the part where you're going to go, oh, really? It's already the first day and you're going to start doing this on me? So 778 foot-pounds of work. All right. So would I ever make you remember that it's 1 BTU is 778 pounds of work? Probably not. I would not. That does not sound like something I want to remember. Therefore, There's other things we can remember. All right, so 1 pound, 1 lb, 1 pound of petroleum. What's petroleum? It's a fossil fuel. It means it comes from fossils, which is the stuff we get out of the ground. So while I'm on that subject, people say you shouldn't dump your oil into the drain. I say it's direct recycling. I don't know. No, don't dump your oil into the water. Somebody's going, you can't say that. All right, 1 pound of petroleum, and oh, by the way, 6 pounds. That's 6 pounds. 6 pounds. Avgas weighs 6 pounds. I'm going to put that here. Avgas. That means aviation gasoline. Aviation gasoline weighs 6 pounds per gallon. So 1 pound equals 1/6 of a gallon. In case you wanted to know how much is a pound. Because you don't buy fuel by the pound, do you? Well, if you flew jumbo jet, you would. Okay. So 1 pound of petroleum. How much is that? It's about 1/6 of a gallon. Can produce about. Because it's going to depend on how much fuel, how much air. Is it lean? Is it rich? We'll talk about that next semester or next 8 weeks. About 20,000 BTUs. Or 20,000 times 778, or about 15,560,000 foot-pounds of work. That is a lot. So that is to say that 1/6 of a gallon should produce over 15 million foot-pounds of work. But does it? Not even close. We start thinking about then thermal efficiency, because when we talk about it, what is the fuel doing? Burning, and it makes heat. Okay? And then the heat expands some gas, and it pushes the piston. So if we stop and we think about what is happening to all of this heat, is all of the heat transferred into work energy? And the answer is clearly no, because if it did, you would go up to a running engine and go, well, that's nice and cold. That thing's running great. That didn't happen, does it? Okay, so if we look at then back to thermal efficiency, we're going to see how efficient an engine is. Thermal efficiency is the percent of work. Am I okay if I roll up a little bit here? Percent of work an engine gets for that pound of fuel. All right, well, let's see where it goes. So for starters, we get about 20 to 30% for power output. So only 20% of this 15 million foot-pounds is actually power. Well, where's the rest of it go? Well, we get about 15 to 20% is heat loss out of the cylinders. Can I scroll up? I need more room. Of the cylinders. So right there, all that heat coming off the cylinders, lost work. 5 to 10% is friction loss. Where do we have friction in the engine? The piston rings going up and down the cylinder walls, the crankshaft and the bearings, the gears meshing, driving magnetos in the back, driving a fuel pump, all that kind of stuff that just doesn't help go power to the propeller. We can say friction loss. And then we have 40 to 50%. Anybody care? Guess where this is going? Exhaust is lost out of exhaust. Well, this is why turbochargers are becoming so popular, is because we have all of that waste going out of the exhaust, and that's where you hook a turbocharger. The turbocharger takes that heat from the exhaust, runs it across the turbine uses the heat energy to turn a compressor, the compressor puts air back in the engine becomes more, not thermally efficient, but it becomes more volumetric efficient. We'll talk about that here. And so that's why we'll get turbochargers next class. I don't think that this part is on the test, so I'm just going to skip it. Thermal efficiency can be computed as follows. Thermal efficiency, well, it's on the test, we'll circle back around. Otherwise, you're just going to go, why are you telling me that? All right. So recip engines are about how much efficient? Yep. So I'll write that. So well, I'm just going to throw this up here, just so you know that I said something about it. So thermal efficiency is calculated, is computed as, and wow, I don't want to do this to you. Indicated horsepower times 33,000 divided by weight of fuel. Divided by, no, I'm not going to do it. We're just going to, it's going to take up too much time and it's not on the test, so you don't care. And now we're going to move on. If you really want to know that, go to engineering school.
It's in the book.
I don't know if it's in their book. Maybe. Oh, it's in the book. Look it up. I'm not going to ask you that. All right. Some of the greatest engine mechanics I've ever known would know how to figure that out. If you want to be an engineer, it's fine. Okay. Okay. So recip engines. Recip engines are only about 34% efficient. 34% efficient. All right. Then I said something a minute ago about volumetric efficiency. And these are all things an engineer has to take into consideration when they're building an engine. The better the engine, of course, the more efficient it is at using the fuel. Like I said, that's now turbochargers. And if we look at well, turbochargers have a lot of function in aviation because we're dealing with altitude and loss of air pressure. So it's really important there. But we look at like where things are going with automobiles, where their technology is way ahead simply because everything for an aircraft has to be proven, and then somebody has to decide that they want to get it approved by the FAA, which costs millions of dollars, and then you have to have a return on that investment, and if you don't get all of that, then it's not worth it. You can just put it in a home built or a car. So where have cars gone? Well, look at Harry, they get all the way into electric, but we'll back up a little bit. You still have your Tesla?
Yep.
Okay, so like I think most cars now are going to direct fuel injection, where we see the intake valve and the engines we're going to be dealing with, the intake valve opens and what comes in?
Air.
Fuel and air already mixed. It came from the carburetor or the fuel injectors. But like my car, it has an injector that actually sprays the fuel right into the cylinder, which aircraft engines do not do. They do not do that because it takes massive amount of pressure. Everybody know what the fuel rail pressure is on a gas or diesel?
Like 20,000.
Yeah, on a diesel, I know diesel's somewhere around the 20,000 PSI range.
Yeah.
Yeah.
That's the injector pressure.
Yeah.
Yeah.
That's what's running through the fuel rail.
Yep.
Through the injector.
Yep. So we're dealing, but aircraft engines, we're not there yet, not at all. So, but anyway, the technology, so you want to get the thermal efficiency up. So if you're spraying the fuel right into the cylinder, you can really control it with the computer, exactly how much you want in, with the manifold absolute pressure sensor. So, okay, here's how much air you're getting, the weight of the air. You need this much fuel to be a perfect blend at this time. Boom, all right. So that's thermal efficiency. But then we get into volumetric efficiency, which is, we'll go back to this. Here we go. All right, so volumetric efficiency, when I've got this thing running here, that deals with, as the piston is coming down, we have this low pressure in here. There we go, coming down, stop right there. We have this low pressure that's been generated here inside of the cylinder, and it's drawing fuel and air in. Of course, somebody would say that it's actually the opposite. This is a lack of a pressure, so the pressure is forcing it in. But I think it's easier to think of it this way. It's a syringe, it's pulling it in, but it's moving really fast, right? So if you consider that an aircraft engine runs at around 2,500 RPMs, that's 2,500 revolutions per minute. Somebody do the math on that. What is that per second? But it's going so fast that this piston is getting down to the bottom and turning around and going back up. And in theory, the valve had already closed. And it was like, wait a minute, you never even filled up. You went down so fast and closed the valve that you only got about half the air that you should have got in there. I'm just making up that number, half. But you got less air inside of this chamber than you should have gotten. So it's all the way down there at bottom dead center. It's still filling, and then boom, it's on its way back up, and the valve's already closed, and this could have taken more if time would have allowed, but it happened too quick. Well, a turbocharger actually, or a blower, if you will, or a supercharger, forces air in, which helps that volumetric efficiency instead of just depending on the piston to suck it in. It's the difference between you breathing in, your diaphragm stuff goes down and you kind of suck in air with a blow, with shop air, right? So you put shop air in your mouth and squeeze it, right? Your volumetric efficiency goes way up. Okay, that's your superchargers and your turbochargers. All right, so we want to get the volumetric efficiency up, and of course, not everything has a turbocharger. A lot of aircraft don't. So engineers think about, well, how can we get more air in there? Well, just if we were a group of engineers and we're developing the first Otto cycle, I'll be Otto. We're developing the first engine. I think, well, we got to get the volumetric efficiency up. What kind of things can we do to get more air into the cylinder? There you go. Make the valve bigger. I never thought about that. Okay, so So if I look at any engine and I've got two valves, I got a small one, I got a big one. Big one, it represents what? Intake. Intake is always bigger because of volumetric efficiency. Well, why is the exhaust smaller?
Back pressure?
Because it's pushing it out. It's forcing it out. Yeah, the displacement is making it leave. So you can make, of course you want your valves as big as you can, but it's easier to make a bigger intake and a smaller exhaust. So exhausts are always smaller, intakes are always bigger. Volumetric efficiency. I was looking for that. I could throw this out just to see if anybody else knows this one. What else could I do? Yeah.
Is there any valve overlap?
There you go. Leave the valve open longer. And we're gonna get to that point, and I'm gonna show you how the valve actually stays open a lot longer. The piston goes all the way down, still not full. It starts coming up, and the engineers figure, when it's about here on its way back up, that's as full as it gets. That's when we're gonna close it. So, but we'll get around to that. All right. So volumetric efficiency. We're going to talk about volumetric efficiency, valve overlap, and ignition timing. Well, that's an awful lot in one thing. I don't know why I did that, but anyway. So, volumetric. Volumetric efficiency, which if I asked you to define volumetric efficiency, I would hope you would have some sort of working definition right now. And how could we define it maybe? What would anybody say?
Filling up the cylinder.
What's that?
Filling up the cylinder with as much air and fuel.
There you go. So we could say it's the efficiency is the ratio or the difference between how much fuel and air does get in the cylinder with how much could get in the cylinder. Like if I stop it, it's going to be full, right? But if I'm running it at 2,500 RPM, it's not full. So I could stop it and say, well, now it's filled up. So volumetric efficiency, how much gets in versus how much could potentially get in. Because I want it full, but it's not going to fill. So volumetric efficiency of a normally aspirated, well, let's talk about, what is the word, if you aspirate, what does it mean you do?
Into a vapor.
No. Come on, you took medical terminology, didn't you?
Yeah, you breathe in your throat.
There you go. You suck in your own sick. That's when you aspirate. It means you puke and then you inhale it. Well, how am I going to know? Okay, so normally aspirated engine, I don't know how I'm going to tie that in. It has nothing to do with your sick, your puke. But normally, so it's the drawing in. So a normally aspirated means that it is non-turbocharged, non-supercharged. There's nothing helping the air to get in. It's just, so it's the same thing as saying non-turbocharged. Yes, Al?
It's not called naturally aspirated?
Yeah, it is naturally aspirated. Did I put, normally or naturally. Naturally aspirated. Aspirated engine is always less than 100%. Now, if I had a turbocharger or a supercharger pushing air in, I could get over 100% because it'll force it in there. That valve opens up. It's like, whoa! Like, again, breathing through a shop air, you know? And you're over 100%. Forced induction is a good word. That's what it's called. All right, so let's see some other rules here. Volumetric efficiency. I should just call it VE. That would really save me some time here. Is greater at wide open throttle what is wide open throttle? Sometimes abbreviated WOT. Wide open throttle. What is wide open throttle?
Throttle plate fully open.
Okay, what's my engine speed?
All the way.
What's that? Wide open. That means foot on the gas, fast as it goes. Because there is literally, inside of the pipe going to the engines, a plate in there that controls how fast the engine goes. And when that plate is wide open, there's less of a restriction. So if you have less of a restriction, it's like breathing through a straw from McDonald's versus breathing through a straw from, I don't know, what else? Taco Bell, I guess. McDonald's has the big straws, right? Or they used to. I don't know anymore. You had McDonald's today? The big straw? Yeah, it's a sewer pipe size, right? So.
Well, technically the quickly smoothie does.
Okay.
The Boba ones, they're like super
Okay, so the engine literally, it's either breathing through a pipe with a restriction on it. Really, at idle, you look at a throttle plate at idle, and you look at it and go, how is it getting anything through that? It is completely and totally closed. It's a very small crack in there. And that's why your manifold pressure is a vacuum. It's literally a vacuum at that point because it can't. So volumetric efficiency is extremely low at idle, and the wider open that throttle plate gets, the faster the engine then is running. It's running faster too. The more efficiency goes up because you remove the restriction. So that means then it is less at idle. It has nothing to do with the speed of the engine, I would think. So also, sharp bends in intake, reduce efficiency. So when you look at the design of the intake pipes from the carburetor, from the carburetor, you want as few bends as you can and really gentle bends going up. So the more sharp turns and snakes it's got to go through, the more restrictions you have, the worse it's going to be. Also, high intake temps. Temps reduce efficiency. Why? Why does hot air reduce efficiency?
It's less dense.
Air weighs less when it's hot. So you're getting literally less air. Air really needs to be by weight, not volume. So even though it's like you're getting the same air, you're completely not. It weighs so much less that if you put the same amount of fuel in, it's going to be too much fuel, because there's not enough air. So high intake temps. How can I get high intake temps? Going way ahead. See if you guys know this. Okay, car beat. How about if it's hot outside? You have less power in your car when it's hot outside because the air doesn't weigh as much. Talked about turbocharger. Turbocharger uses a compressor. When you compress air, air gets hot. So you add a turbocharger, you're going to get hot air, which means lower efficiency, but you just push more in it to compensate for that, to a point. All right, so what else can we do? We talked about this a little bit. What else can we do to increase volumetric efficiency? Well, I could bolt on a turbocharger or supercharger, but that's not always possible because, like, I have a little Cessna with an O200, and if I look at the type certificate data sheet, it never came with a turbocharger. So I can't bolt on a turbocharger. Well, actually, I can't do anything, but what can an engineer do? Well, so to increase volumetric efficiency, this time I'm going to abbreviate VE, volumetric efficiency, valves open and close at times other than at TDC and BDC. So in other words, I go back to this little animation that we have, and every time when I watch it, when does the intake valve open? Right, top dead center. It's perfect. It's like, okay, the piston starts coming down and it opens up with it. Then the piston gets to the bottom, and when does the intake valve close?
It's right after it starts to come up.
As soon as it starts to come up, boom, it closes. And then it comes up, and then it has the spark plug right at the top. Then it comes down. That's the power. Then it starts to come up. And when does the exhaust valve open? The minute it starts to come up. And when does it close? Oh, when it's at the top. It doesn't work that way for a lot of reasons. One, if we really, just in short, if we really did operate the intake valve like that, you're going to kill your volumetric efficiency. You're shutting the valve before the air had a chance to actually fill the cylinder. If we wait to open the exhaust valve until the power cycle is all the way down to the bottom, you have really hot gas in there that is no longer doing any work, and now you're just keeping it in the cylinder. So what does that do to the cylinder temps? It's gonna melt it. You got to get rid of it. That stuff's 1,500 or more degrees. It's off the top of my head. So you got to get rid of it. So the exhaust valve's open and says, "Well, you're done doing your work. Go. Get out of here. We don't want you around anymore. I don't like your kind." And so that's what it says. I don't know. Don't blame me. All right. So let me see. 1, 2, 3. Right here. So a couple of words here. Valve lag. Valve lag is opening or closing after TDC or after BDC. In other words, late. Later than what we saw in the little video. And we can have valve lead. And that is opening or closing. Opening or closing before top dead center or before bottom dead center, which is early. So you just look at it and go, wow, that was earlier than what we first talked about. That's valve lead.
Doesn't it say valve lead?
What?
Valve.
Valve?
Oops, yeah. Just work with it, would you?
Sometimes your eyes will be A's, okay?
All right, I believe this is one of your Q&A questions. What is duration?
How long is this?
Yeah, it should be duration, how long something is. But this time you have to figure out how long what is. How long, that is, duration is the time valve is off its seat. Open. Open. Scroll up, write that here. Off its seat is open. All right, you ready for something to get real here for a minute? Let me see. I don't think I kept that picture here. In your book, I'm getting these numbers from your book, and you have a drawing that has a bunch of circles in it. And it talks about valves in these circles. And I looked at that and I thought, oh my goodness, there's got to be an easy way. So I'm going to do the same thing, but I'm going to do it linear. So intake valve. And this is coming, and I wrote, this is the valve timing that your FAA book publishes. This is not a specific engine that I'm aware of. So when you look at it, don't go, oh, I wonder what engine he's talking about. I don't even know what engine I'm talking about right here. So according to this, let me see. Let me see. Well, I'll write it and then we'll just go with it. So according to this one, it shows that the intake valve, so intake valve, what does it do? It opens 50 degrees before top dead center. Again, I don't know if this is even a real engine. It probably is, probably a radial or something. And why does this happen? Well, don't want to do. You know, I'm going to try something else here. We'll just come back around to this because I think I can do this better without words and do a picture.
It's in crankshaft, 50 degrees, right?
Yes. Let's try it just with pictures here. All right, so this is how I want to do this. So we have 4 strokes. We have intake, compression, help me out, power, exhaust. Okay, so each one of these is going to be a stroke. Oh, I know what I should do. Sorry. You need to kind of... Just going to move it over a little bit. Intake, compression, power, exhaust. What comes next? Intake. What came before? Exhaust. So here's exhaust. So it's kind of going this way. Right? It doesn't circle around. It's just, it's coming from somewhere. So I can go after a little bit, before a little bit. So on the intake stroke, which way is the piston going? Down. Okay, so it's, okay, this is top dead center here, TDC, and this will be bottom dead center here, and it's going to go down. I'm just going to do a diagonal to show that it went from top dead center to bottom center, and it's going to go compression, and then power, it's coming down, exhaust, intake, and then that means that it came from over here. So there we go. So that's the, can you picture this, the piston going up, down, up, down, up, down? Yeah. Okay. So then I want to look at where do the valves open and close? So I'm going to let blue be my intake, all right, because blue is cold and it's the colder one. So we said earlier that the intake valve opens right here at top dead center, and it's open through the intake, and then it closes right here, right? That was kind of our dummy way of doing things. Yeah. Not dummy, it's a bad word. Our simplistic view of things. And I'll let red represent the exhaust because red is hot. And the exhaust valves are very, very hot. And so we said it's open during the exhaust. So open during the exhaust. All right. Okay, so if we look at that, and hopefully that drawing is making sense for you, there is no valve overlap. Because valve overlap is defined at the time both valves are off their seat. Are the valves ever off their seat simultaneously? No. Okay, so if we go back then to this drawing in your book, you probably can't see, but there's that little drawing right there, and it's got a circle, and I won't even try to draw it because I'll spend too much time. You're like, yeah, whatever, it's in your book. And I could pull it up real quick, but I'm not gonna. So it says that this is what actually happens, according to this. It's saying that to increase volumetric efficiency, what we want to do is we want to open the intake valve before it's time. So when? About 50 degrees before. So this is what? This is from here to here is how much? From here to here is how much? 180. So this is 90. So halfway between 45, a little more is about 50. So that's about 50 degrees right there. So intake valve is now going to open 50 degrees before top dead center. So which stroke did it open in? Exhaust. So I'm going to make the same thing over here, right about there. Just because it hit that diagonal line doesn't mean anything. All right, it just shows the diagonal line. Just shows the piston was going up, and now it's going down. Now it's going up. Now it's going down. Now it's going up. It's going down. All right, that's all that's about. Okay, so it says that. Well, why is it doing that? All right, so we'll talk about the opening first. So this allows the low let me see. Intake valve opens 50. Forget my notes. All right, so what's happening then is we can go back to this. We can maybe make this work a little bit, kind of slow. I'll slow it down a little bit. And by opening up that intake valve earlier, see what's happening is we'll get it to the right stroke here. Okay, intake valve's opening, and it's going to get down to the bottom, and then in this animation, the valve is instantly going to start to close. One frame, it's closed. But what's happening really is the piston there at bottom dead center, it is not filled up full of air, which we talked about, which means it has poor volumetric efficiency. It doesn't necessarily poor, but it's just because of it. So it's not even full, not even close. Well, if we keep that intake valve open, which won't on this slide, and wait until the piston is coming back up, there's a point where an engineer has figured out at the right RPM that when the piston is coming up, right about there, it's pretty well full, right? Because we have all kinds of things happening. First, we have the suction, and you're thinking, well, wait a minute, is the suction still there? Well, a little bit, because it didn't fill up, but we're losing that suction, but also there's inertia. This air is moving in, and we have to suddenly stop it. Well, why? If it's got inertia coming in, we can wait until the suction is gone, but the inertia of the air coming in, it's enough to fill a little bit more. So it's filled a little bit more. Also, an aircraft, they're designed so that the air scoop with the air filter is not only facing forward, but it's usually behind the propeller somewhere. So you have the force of the aircraft going forward, which is called ram air, plus the prop wash pushing in, which is kind of like a little bit of a turbocharger right there. So take advantage of that stuff and you push it in there. So that's why you want to open your intake valve earlier than normal. Well, okay, so we look at it there. So if it closed too early, we'd lose, or closed later, we'd have all this volumetric efficiency loss. Then your book says that it closes later. It doesn't close here. Well, it opens early, and it closes later, which is, I think, really what I mostly explained right there. So that's at about 30 degrees, and, oops, it opens at 50. Closes at 30. Well, I didn't explain. I just explained why it closed late. I didn't really explain why it opens early. All right. But in order to do that, I got to explain something else. So why does it open so early? Here we go. All right. So exhaust. Okay. And now it's not going to open until it's there. But this book is saying, wait a minute, it's open way down here. What the heck's going on? Well, what's happening is, again, we'll talk about inertia, and we have all of this exhaust leaving here. So I'm on the exhaust stroke, right? So we'll go back here. Now I'm going forward. The exhaust stroke is pushing all that nasty stuff out. I'm going to go backwards a little bit. All right, but if we open this nice and early, what happens is the exhaust is on its way out, all right? But let's open the intake valve and allow some fresh air to come in. So one, that's going to help sort of push out the exhaust. But the exhaust also has the inertia leaving, which kind of creates a bit of a vacuum. And so it draws in the fresh air. So open it up early so we can draw in fresh air, help get rid of the exhaust because of the inertia of the exhaust gas leaking. And it helps also with the exhaust called scavenging. Scavenging means to get rid of the nasty exhaust gases, because we can circle back around and talk about volumetric efficiency. Well, what good is it going to do to get fresh fuel and air in there if the cylinder is stuffed full of exhaust. Got to get rid of the exhaust before you get the good stuff in, right? Got to breathe out before you can breathe in.
So
You shouldn't have to, but
there's a brief moment, there's a brief period of time where both valves are open at the same time?
sort of.
Like a
Okay, I'm going to say
micro
sort
second.
of. Yes, you're 100% accurate. But I'm going to tell you a secret. This is going way advanced. I'll come back around to it, but I just want you to know that I know this, and you're going to know this. Whenever you build an engine and something doesn't go quite right with the engine, I don't care what it is, doesn't start right, it doesn't idle right, the first thing everybody's going to say to you if you built it, you mistimed the cam and crank. I don't know why they go there, right? 100% of the time. Okay, probably not, right? That's very simple to get those two gears meshed. Never seen anybody do it wrong. Maybe I've seen a few students do it. But so Lycoming says, hey, we know this. Here's a simple test to find out if your valves and your crank are perfectly aligned. So you go to one side of the cylinder and you bring it up on top dead center of compression. Where are the valves? Right there.
Closed.
You are correct. They're absolutely closed on compression. The other side of the cylinder, remember it's a boxer. So what's this piston over here doing? It's the opposite of that. So it's on top dead center, but it's not on compression. Therefore, it's top dead center of what? Exhaust and intake. So if there was valve overlap, what would I see there? Two open valves. Lycoming says the simple way to tell if the cam and crank timing is off, put that cylinder over here on top dead center of compression, come over here, and both valves will be closed. And if you move the propeller even the slightest bit in one rotation, the correct rotation, then it's going on in. You should see the intake valve start to open because it's starting its intake. Go backwards and you'll see the exhaust valve. And that means that they're doing this. So that tells me there's how much valve overlap. None. Hey, that's just Lycoming, right? They don't say that, but read between the lines. So do all engines have valve overlap? Apparently not. And that is not just the Lycoming 290. That is Lycoming engines. All horizontally opposed. So, all right, so back to this.
I don't know. I was always under the impression that
Well, you're wrong.
there's way through valves. I don't know. I guess. I don't know.
Just telling you what I know. Maybe I'm wrong. I could be wrong. You prove me wrong.
When valve,
Ah.
I always thought I saw that piston over there with the valve stuck in it like this.
Yeah.
Where they had it's a tragic love story right there, but I don't know.
Oh,
Whenever I
that's-
think of valves opening and closing at the wrong times, that's what I think of.
That was the one that broke. Okay, so we're talking about the intake, and now we know, according to this, and a lot of engines, that the intake opens on which stroke? Exhaust, and it closes on? Okay, that now becomes a test question. When does the exhaust valve open? It opens on which stroke? Exhaust. Okay, forget about the Lycoming story I told you because all of your test questions, all of your FAA questions assume this. They don't know about that. So you'll know about that, but they don't know about that. All right, so intake valve opens, is blue is the intake valve. Intake valve opens on the which stroke? Exhaust, and closes on the compression. Okay, let's talk about what your book said about, let me get the numbers. It's exhaust valve. What about the exhaust valve? Is it just doing this little thing right here? No, it's going to be equally as messed up. So, exhaust valve opens about 30 degrees before top dead center. Opens about, 30 degrees before top dead center. That's going to put it right here into which stroke? Power. And it is going to closes about 25 degrees after. So that's 25. And I said this was, we'll make this 30. And back to here. This one was 30 after, which we don't have, but this one is 50. 50. And so we can look at this and go, wow, oops, I got to fill this in over here. So this is exhaust into intake. We had 25 degrees, 25. So if we look at this, we'll let green be this, I have valve overlap between here and here. Between here and this, then, is valve overlap. All right, so again, why then do we have the valve overlap for the exhaust? Okay, so it's going to open pretty early into, well, I'm sorry, it's rather late. It's 30 degrees before top dead center. So it's not that many degrees, right? It's, let's see, we can go back to this. What is 30 degrees after top dead center? So here we go. Oops. Okay. Exhaust comes up, and what did I say? 30 degrees. Oh, it's on. Can I get a whole thing out of it? Power, no. Power, compression, so power, intake, compression, power. Okay, so I said it's going to open 30 degrees before bottom dead BDC, 30 degrees before it reaches the bottom on power. So 30 degrees before it reaches, so 30 degrees, it's about, if we look at this, there's 90, there's 45, so it's going to go a little bit more than even that. Well, it just isn't going to let me go into that range. Yeah, it's like, well, let me go in the range. So it's getting close to the bottom and not quite. Okay, so why do I want to open the exhaust valve early? Get rid of that nasty hot gas. All right, it's done doing its work. So you have this gas that is expanded. It's pushed on the piston. And if, I don't know, sometimes I make up things. Okay, so it's kind of like it's pushing on the piston, but at a certain point, the piston is now going at the same speed as the gas. So if it was doing that, how much work is the gas doing? None. So get rid of it. Go. Get out. Because if it stays in the cylinder, it does what? The cylinder heats it up, starts melting the piston, just making a mess of things. So might as well, if it's done doing its job, get rid of it. So it's going to open it up right there and let it start working its way out. All right, relieve that pressure. So it does that. And then why does it take so long before it closes? Yeah, it's got inertia going out. It's helping with volumetric efficiency. We want it open and let the fresh air, it gives the fresh air, the way I view it, the fresh air kind of a path to go through. It's like opening windows on both sides of the room. So if I leave the exhaust open over here, then, and I open the intake, it's going to want to filter in more. So thing is, we just got to close it before we let the gas out. Otherwise, we get gas in our exhaust, and then it flames. It's really cool. So, yeah. All right. So that's what's happening there. Steve, you've been quiet. Wow, what's up?
Aren't there, like,
Did you just wake up?
I noticed on like a lot of newer aircraft, it would adjust the mixture. It would adjust the timing of the valve, so you get the most, I guess, bang for your buck.
I do not think that is true.
So how does that work? Because I see on like the gauge where they.
There is no, to the best of my ability, there is absolutely no variable valve timing recip engine on the market. The most highly advanced recip aircraft engine on the market is the Lycoming EMC. I forget what. Do you know what it is? I've got it, but it basically it's an electronic version of what we normally have. The only thing that is variable is the ignition timing. So you can adjust, and a lot of aftermarket electronic ignitions are available, but you can adjust the ignition timing. But there's no variable valve timing in aviation yet.
It doesn't have magnetos.
You take one mag off and put a electronic ignition on one side, turn off the mag, and then you run off electronic ignition, which can advance and retard, and then if that fails, you turn on the magneto.
Yeah, the sporties, and they said like get more power out of each stroke by adjusting the time. I was like, what
Timing, it's ignition timing. Yes, that is true. That is very true. All right, and what he's talking about, okay, so where does the spark happen? Well, spark needs to be yellow. So where does the spark happen? Well, in the video, spark happened where?
Right there.
Intake, intake down, you compress it, it happened right about here, right?
Yeah.
Okay, now it's got to happen over here. About 25 to 30 degrees before top dead center on the compression. And, well, I guess it's about time to go, but I'll just finish this thought. And the reason why is because if you waited till it was top dead center, then again, it's like the flame front's chasing the piston, and that doesn't do anything. So you start the flame front way before it starts to grow, and it doesn't happen instantaneous. It's got a speed to it, and while it's starting to grow, the piston's going to come up and catch it, compress everything, and then from then on out, man, it pushes. So in your car, this timing moves all over the place. because the computer allows it to. Or even in the old days, we had vacuum advance or flyweight advance, which would move it. But in aircraft, we don't. It's fixed. It's just sit right there. It's only recent technology that is allowing it to start to move a little bit to be more efficient. So, all right, well,